Again, the return predictability says that the expectation of future return based on the current information depends on the current information, that information. Now, what kind of variables do you think can have good prediction power for future returns? The most famous one, the most well-known candidate is dividend yield. That is the total amount of dividends paid during this period divided by the price at the end of the period. Now, the reason why people suspect that this variable might have prediction power for future return is very simple and naive. Currently, the asset or portfolio is paying this much dividend. Let's assume that in the future, this asset is likely to pay the same level of dividends in expectation. Okay? If the current price is small compared with that level of dividends, it almost indicates that investors, for some reason, investors are discounting future payoffs a lot. And that's why this dividend, if the dividend is large, if people expect lots of dividends in the future, let's assume that the future dividends are likely to be similar to current dividends, okay? If people expect high dividends in the future, and yet if the price is low, yeah, it sounds like investors are discounting the future. Investors are requiring a lot of return, expect return from this asset. Yeah? So let's focus on this dividend yield. So this is called dividend yield. It's inverse of price-dividend ratio. And a lot of people regressed the return series on the dividend yield series. Here's why. Suppose you regress the return series on price-dividend ratio, dividend yield. So think about the following regression. The return is equal to some constant alpha plus some slope times the dividend yield in the preceding period. The information should precede the return. Otherwise, it's not prediction. Plus some error term. If you regress this, if you do this regression, and if you find that this beta slope is significantly non-zero, that's the evidence, that's an evidence of return predictability. Because in that case, if beta is not zero, then the expected return given this particular information, dividend yield, depends on this currently available information. Does that make sense? Well, in general, it doesn't have to be dividend yield. You regress return on some preceding variable. If you get significantly positive slope, it sounds like that variable has some prediction power for the return. So let's do such return predictability exercise. Okay, here's the return predictability exercise. It's very simple regression. It's just regression. we are going to use two different data sets. One is yearly data. So it has 77 periods from 1926 to 2002. The first column is just date. The second column is dividend yield. That is the dividends. Okay, this is not a particular asset. This is a broad-based market portfolio. This is a CRSP value-weighted market index. So it's a very large portfolio of many, many companies. The second column is the dividend yield. That is the total dividends paid during that year divided by the price of this asset at the end of the year. The next column is the annual return in the subsequent year. Okay? And the next is, so this is 1 year return, so that's a relatively short-term return. And the last column is the long-term return, that's 7-year return that realized for the 7-year period following the observation of this dividend yield. Is it okay? Yeah? And we have one more data set named predictability quarterly, comma-separated values file. It's the same date, dividend yield, quarterly return in the subsequent quarter, and the 7-year return. But it is a quarter return, so it has more periods. Each year has 4 quarters, so we have 308 periods for this quarterly data. And I load these data files using this read table function under the name of, okay, let me load the yearly data under the name of my data y, and I load the quarterly data under the name of my data q. And I say, okay, let's first use yearly data for our regression, and let's use the short-term return. I say the second column is dividend yield, the third column is 1-year return, and the last column is 7-year return. So far so good? Okay, let's do regression. So I store the regression result under the name of my coef. So that's coef function of summary function of this linear regression model in which I regress annual return on the dividend yield in the preceding period, and after running, my coef is this regression result. So I say, okay, A is estimated slope, 1 element, B is, estimated intercept, and B is the estimated slope. That is 2 element. And TB is the t-value associated with this slope estimate. That's 2, 3 element. And let me plot dividend yield and subsequent annual return with plotting character number 20. So it's like this. Okay, the horizontal axis is dividend yield. The vertical axis is the subsequent annual return. I can add the estimated slope points, dividend yield, and A plus B times dividend yield. Plotting type is L as in line, and color is blue. let me add the t-value associated with this slope estimate in the main title of this plot. So main equal t-value is TB. Okay, TB is the t-value of this estimate. So it has too many decimal numbers, so let me round the t-value using round function so that it has only 3 digits after the decimal. Okay, so if we regress annual return on dividend yield using this data of 77 years, we have moderately positive slope with, yeah, it's moderately statistically significant. Yeah, and we can do this exercise for the long-term return. 1 year return is relatively short, but in a short-term return like 1 month return, quarterly return, 1 year return can have lots of noise, ups and downs. But if you look at the longer-term return, you know, this predictability may be stronger. So let's use this 7-year return. So I say long-term return. And instead of R1, I use R7. And when I plot dividend yield and this long-term 7-year return. Let me open new window. You should use quotes instead of windows if you're using Mac. And then it looks like this. The dividend yield and the subsequent 7-year return, it has positive relation, and the t-value is 4. Okay? And you can do the same exercise using the quarterly return. And that's part of your exercise for this week. Is it okay? Do you understand what we are doing? Okay. A lot of people did this regression. After all, it's just regression, and the topic is interesting, so you can imagine that a lot of researchers all over the world did such regression. Of course, the actual regression method can be a little more sophisticated than what we did today. And the finding is that, okay, the dividend yield seems to have some prediction power for the following, for the subsequent, well, for the return, for the future return. And that prediction power is stronger for longer-term returns, long-term returns. But there is a caveat for that. Ferson and 2 other people, so let me write Ferson et al. It's 2003 paper published in the Journal of Finance. Says that, okay, people do regression, regressing return on some other variable, such as dividend yield, and get some significantly positive or negative slope. But those seeming predictability That is to say the t value greater than 2 or smaller than negative 2 may be due to two things. One is data mining, and the other is spurious regression. T-value equal to or negative 2 means what? That's 5% significance level. If there is no prediction power at all, then such t-value should happen only 5 out of 100 times. Yeah? And t-value of 2.7 is the 1% significance level. And such high t-value should arise if there is no correlation or prediction power at all. Such a high t-value should arise only once in 100 times, approximately. Yeah? And data mining means what? If you just regress on dividend yield, it's okay. But if you try like 100 or 1,000 variables, like interest rates and this and that, price-earning ratio or temperature or the king's mood, okay? Again, there are thousands of researchers in finance all over the world. They try 1,000 variables. It's possible that once in a while, they get some significant, statistically significant predictive variables. Yeah? That's what data mining means. Is data mining okay? Yeah? Should I write it? It's okay, right? I don't have to write anything. Spurious regression is what? Spurious regression, you have heard of spurious regression in econometrics course? No? I think, well, you might. But spurious regression is as follows. Let's say there are 101 periods, okay? And suppose x1, so there are two processes, x and y, okay? And suppose both x and y are 0 at the initial date. And after that, let's say both x and y follow a very persistent autoregressive process. Okay, let's suppose that both x and y follow AR1 process with the autocorrelation parameter very high, 0.9. Okay, that is okay. Xt plus 1 is equal to 0.9 times the previous value of x plus error term, which is IID. Let's say this error term follows some standard normal distribution. And same for y. Next value of y is 0.9 times the previous value of y plus the error term for y, which also is a random draw from the standard normal distribution. Imagine such a situation. So x and y are highly persistent, but as you can see, x and y have no relation at all. Imagine such a situation. Is it okay? Now, okay, x evolves on its own and y evolves on its own. x and y, we know that x and y have no association at all with each other. But suppose we plot x and y at the same time. That date 1, both x and y starts from 0. And if the shock in the second period is positive for x and negative for y, they move in this direction. So this is t equal to 1. And they might move to this point at t equal to 2, t equal to 3, t equal to 4, or t equal to 5, and so on. Suppose there are 100 periods. In such a situation, it is known that when you regress y on x, even if x and y are completely independent from each other, if both x and y are persistent processes, there is very high chance of getting statistically significant slope. And this is called spurious regression. That if you regress y on x, then there's a high chance of getting statistically significant relation between x and y. And this is called spurious regression. So the point is that high t value may be spurious when both x and y are persistent, not IID across samples. I mean, in your usual econometrics, it is assumed that the samples are IID. Okay, there's IID across samples. But if samples are not IID but persistent, then when you regress y on x, even if you get significantly positive or negative slope, you should be careful about the interpretation because there's high chance of spurious result. Okay. So, spurious regression simulation. So let's say n is 100, and both x and y are series of 101 periods. So initially x and y, I just make them initially as 0, 0, 0, 0, 0. Let me make them have 101 components because that will make our task simpler. And okay, we are going to generate this AR1 process for x and that for y, and we need every period we need some shock. The shock for x is 100 random draws from the standard normal distribution. Mean is 0 and the standard deviation is 1. And same for y. uy is the error term for y, and that's random draws from the standard normal distribution. Okay, so after that, x is just 0, 0, 0, 0, 0. Y is also 0, 0, 0, 0, 0. E of x is the 100 draws, random draws from the standard normal distribution. And I say, OK, for t equal 1 to 100, the date t plus 1 value of x is 0.9 times the value of x at date t plus date t error for x. Similarly, the date t plus 1 value, the value of y at date t plus 1 is 0.9 times the value of y in the previous period plus date t error for y. Okay, we are simulating this persistent AR1 process. Yes?
Is it error period t or t plus 1, or is it the same?
It's, yeah, it's, well, notation is a little different from the econometrics notation, but for this exercise, I think t is better because t is from 1 to 100, and this error term u of x has only 100 components. If I want to say t plus 1, then the first component of u of x won't be used, and I should have the 100 first component of u of x. So, yeah, so notation is a little different from econometrics, but don't worry about that for this exercise. And yeah, that's it. If I run this, x is, yeah, x now looks like this. It starts from 0 and it evolves. I can even plot x using plotting type O. That's the combination of points and lines that connect these points. So this is the evolution of x in this simulation. I can add the evolution of y. Okay, this is the evolution of x. This is the evolution of y. And as you can see, x and y have no association whatsoever. Yeah? Let's regress y on x. So I say my coef is coef function of summary function of linear regression model in which I regress y on x. And after that, A is the estimated coefficient. B is the estimated slope. And t value for B is, yeah, TB is the t value for the slope estimate. And OK, let's plot x and y together. Let me use plotting type O, points connected by lines, and line type number 2, it's going to be dashed line, plotting character number 20, and I add the estimated slope. Well, first let me run this. this is the evolution of x and y. It starts from 0, 0, and x and y independently evolves. Yeah? Let's add x and a plus t times x as a line, L as in line, and let me add t value in the main title. So main is t value equal tb, and let me round up the t value to have only 3 decimals. So now, and if I run a couple of times, okay, significance level. I mean, we know that x and y are completely irrelevant, but once in a while, we are unlucky this time. Oh, once in a while, I mean, look at this. X and y, if you forget about this path, and if you just look at these points, I mean, x and y have clear negative relation, okay? But we know that they are not associated at all. Let's do this simulation more. Let's make it longer, 200 periods. And let's do this simulation 100 times. So m is 100, and this is the number of simulation. Every time I generate x and y, I regress y on x, get the slope, get the t value. And I'm going to store the t value every time. So I say, okay, my t value for the slope b is just 100 or m zeros. And do the following simulation. For j equal 1 to m, repeat the whole thing. $100 times. And in the end, store in the jth element of my TV the t value. Yeah? And I can even open a new window every time. You don't have to, but I can do that. Run. Okay, we did a 100 simulation. Let's see. T value 3, minus 3. If you get stuck with designing new Pokemons, probably you should run this simulation. It looks like some character. So. Okay. Let me show you histogram of my TB. Okay, let me close first. Okay, out of 100 times, the t value was between 2 and 4, like around 15 times. 2 and 4, around 10 times. Between -2 and -4, like 15 times. And sometimes the t value was like 5 or 6 or 7. And if x and y are independent across samples, t value like 5 or 6 doesn't happen if x and y are not associated at all. Okay, so this is called spurious regression. So that's their statement, okay, you regress returns on some information, some other variable, you get statistically significant slope, and you say, okay, this variable seems to have prediction power for future returns, but you shouldn't jump to that conclusion. It might be because of spurious regression. Typically, these predictive variables, the candidates of prediction, such as dividend yield, typically have high persistence. Return itself doesn't have a high persistence, but if you think about long-term return, if your data is annual data, and yet your return is 7-year return, one return is from 2000 to 2007, the next return is from 2001 to 2008. Yeah? So these data has some overlap. So return process also has some persistence, so it's subject to spurious regression. And on top of that, there is data mining. Lots of people try lots of variables. So in principle, return predictability is very possible, but empirical finding is mixed. And that was our last topic of finance.